Hello everyone, let's continue the discussion about the VSEPR, and now the next step is using the simple but elegant VSEPR theory to predict the shape of the molecule. Let's do a little bit of recap from the previous Volcast on the VSEPR theory and the electron group geometry. You can take in a formula of any molecular compounds or polyatomic ions and write the proper Lewis structure and get this ABXEY notation. A represents the central atom, B is the surrounding atom, and the E will be the lone pairs on the central atom. And as you can see here is carbon dioxide. You will have Ab2E0, E0, the total number of electron groups will be 2, CH4, the methane will be Ab4E0, the total number of electron groups will be 4, and the list goes on. Ammonia, Ab3E1, total number of electron groups 4, water H2O, it will be Ab2E2, also the number of electron groups is 4, and since the list goes on, the phosphorus pentachloride, Ab5E0, total number is 5, SF6, that will be the Ab6E0, total number is 6, the X plus Y subscript in the ABXEY notation. It's representing the total number of electron groups on the central atom. Here's an even longer list. The boron trifluoride, the bromine pentafluoride, and this IF4 -1 charged polyatomic ion. And also the notion of those electron groups, they are all negatively charged, and they actually are full with electrons, bonded electrons, so they are not going to accept any additional electrons. So the interaction between the bonded valence electrons or unbonded, unshared, unbonded, or sometimes referred to as lone pair of electrons on the central atom, they are linked with the central atom. They're going to repel each other very strongly. And is that repulsion is kind of contribute it to be the determining factor in controlling the molecular shape. And this is called valence shell electron pairs repulsion theory. And here's a link to the Java simulation, and it's demonstrated very clearly. Because of the electron groups strongly repel each other, they want to maintain as far away the distance as possible from each other, but however they cannot get totally away from each other because they are all connected on a central atom. So this strong repulsion and the desire to maximize the distance between the electron groups determine the shape of the electron groups. Subsequently, we're going to discuss in this podcast the shape of the molecule. And also let's recap. Here is the more appropriate representation of the electron groups with these pictures as compared to the previous Volcast. Previous Volcast, they used the bars connected with balls with the central atom to show this electron group arrangement. But more appropriately, they should just use those electron clouds. And as you can see here, if you have the electron groups, you have 2 electron groups, those 2 electron groups are represented by these 2 lobes, and it has to line up on the line. It's a linear shape. The degree between those 2 is 180. If you have 3 electron groups, there will be the kind of equilateral triangle here, and this is called the trigonoplanar. And if you have 4 electron groups, this is called the tetrahedral, and the bond angle becomes smaller. Not bond angle, the angles between the electron groups becoming smaller. It becomes it comes down from 180 to 120, now to 109.5. If you keep on adding the electron groups to the central atom, in this case, the next step will be 5, and now you'll have what we call the trigonoplanar. These 3 is on the equilateral triangle on the same plane, and these 2 are perpendicular, kind of going through the plane. This is how you use the drawing to represent that. Remember, the one with the solid shade is pointing outwards, out of the displaying plane here, and the dashed line will be going inwards. So now it's further increased to 6 electron groups. Now it's getting really crowded, and those are the square planar, and got 2 going through it. The angles, I have 2 angles. The angle between this and those 3 on the plane will be 90 degrees, same thing with the bottom one. However, the one in between the 3 on the same plane will be 120. And now here, looking at when the electron groups goes up to 6, all the angles become 90 degree. And then let's see how this is related to the shape of the molecules. Let's go back to the Corrado simulation, University of Colorado simulation, and you can see here we have a central atom. If we have 2 electron groups as represented here, you can see that's going to be a linear shape because they want to get away from each other. However, if we see those electron groups are connected with the atom, so now we're going to use one connection and add another connection. So you can see here, and it's easily understandable, that will be linear. As we can see, if we have 3 electron groups on a central atom, you will have a trigonoplanar shape, and if those 3 are all linked with surrounding atoms, and you're going to form AB3E0, and then this is going to be 3 of surrounding atoms. The angle between the bond, it's called a bond angle, it will be 120 degree. And if we remove the 1, this bond angle, if we only have 2, AB2E0, and this is going to be a linear 180 degree. So let's see, this is equilateral, but if I remove 1, replace it with a lone pair, and now you can see actually it's assumed close to equilateral, and it's still a triangle, but because this is just a lone pair on the central atom, when we talk about shape of the molecule, we only talk about those 3 atoms. As you can see now, the shape is a bent shape. It's a bend shape. And here comes a fairly important concept. And as you can see, the bond from here is also a pair of valence electrons. And now that pair of valence electrons is controlled by both the central atom nucleus and also the surrounding atom nucleus. Then you compare that to the lone pair on the central atom. And this lone pair is only controlled by the nucleus of the central atom, so it's kind of slightly less controlled. So hence this lone pair of electrons occupies a larger space. The consequence for that will be squeeze this 2 bond further down because they repel very strongly. So the bond angle is not 120 degree anymore. Is becoming less than 120 degree. Okay, so you can pause and digest the torrent of information a little bit as we can elaborate it. And the lone pair plays an important role in determining the molecular and the shape of the molecule. So let's build even further up. If we have 4 electron groups total, and we did this exercise before, and now you can see this is a tetrahedral. This is a tetrahedral because of the repulsion between the electron groups. But if those 4 electron groups are connected with surrounding atoms, there are 4 of them, and now you're just forming a perfect tetrahedral. And also you can see on here, this is electron geometry, and this is molecular geometry. But if we removed, but also the angle between those bonds in a perfect tetrahedral is 109.5. If I remove one, it turns into a trigonal planar, and but just add a lone pair. As you can see here, now is the 3 out of the 4 electron groups are connected with the surrounding atom. Those are used to connecting the surrounding atom with the central atom. And however, the lone pair on the central atom is pushing everybody down because those bonded electrons do not like the lone pair. They repel each other very strongly, so they want to stay away from each other. Also noted here, because of the larger size of the electron cloud for the lone pairs, for the particular reason, there's only one nucleus controlling, which is the central atom. And it's becoming slightly larger. And the larger, for the consequence, it will squeeze those bonds down a little bit further in. So the bond angle in this case is AB3E1 will be less than 109.5. It's roughly about 107.5. So how about we take away one bonded electron and add another. So this one will have the AB2E2 notation, and from the electron group geometry perspective, it is still a tetrahedral. But however, for the molecular shape will only count the 3 atoms. Those 2 pairs of lone electrons are on the central atom. The central atom has nothing to do with the surrounding atom. So the shape of the molecule, it is actually bent. As we said before, the effect of the lone pairs of those electrons will push, because now I have 2, so we'll push down those bonds even further, or even closer together, hence reducing the bond angle. And for instance, we can actually take a look at the real molecules. So if you're looking at water, the bond angle is about 104.5. Let's take a look at ammonia, and this is the ammonia because with this lone pair, the bond angle is 107.8 instead of the 109.5 as a standard for the complete tetrahedral. So you can actually see the electron geometry and the molecular geometry. Actually, for those 4 together, we'll call it trigonal pyramid. So let's continue with that, and now we add 5. 1, 2, 3, 4, 5. So now you can see actually those 3 on the equilateral triangle plane, and those 2 are going perpendicular to it. This is maintaining 2 bond angles. This is 120 and this is 90. This is 120, this is 90. This is called trigonal bipyramid. Electron geometry and also the molecular geometry, they are the same, trigonal pyramid. But if we take away one, and now we're putting another one, and this one is kind of a rather strange shape, and one thing you can looking at it is this by manipulating, and it looks like a sawhorse. It's look like a horse. It's like a sawhorse, a horse. So it's called trigonal by pyramid. That's the electron configuration, because that's also have 5 electron groups. However, because of this lone pair and the molecular geometry is also called a seesaw, or sometimes people call it sawhorse. So the angle, the bond angle, because of this, it's going to be slightly less than 120 and slightly less than 90. Sometimes in textbooks, actually, because of the magnitude of the influence of the lone pair is relatively weak. So sometimes textbooks actually maintain the 120 and the 90 degree bond angle. But I would like you to understand, because of the difference between the unshared valence electrons, it's called lone pairs on the central atom, and bonded electrons, those bonded electrons between the central atom and the surrounding atom. So I want you to know the difference of that. So let's move on. If we take away another and add another electron pair, pair of lone pairs, now you can actually see it's replacing the other one on this equilateral triangle, and this is most likely look like a molecular model. It's geometry. It looks like a T shape. It looks like a T, and there's also some effect on this lone pair of electrons. Is slightly less than 90 degree. So then we continue the trend, take away another one, and adding another lone pair. As you can see, it starts to arrange it, and now we have all the 3 spikes of that equilateral triangle being replaced by lone pairs. Now the molecular geometry is linear, and the bond angle is 180, as the electron group geometry is still trigonal bipyramid, because you have 5 connections. So that finished 5 and 6. Then we have, let's count how many we have. So that's only 5 and 6. If you have 6, you can clearly see, instead of a equilateral triangle, now you have a perfect square, and I got 2 go through it. The perfect square goes through it. So if we have all of those 6, connected with surrounding atom, as indicated by here, the silver balls, and now we have a structure is called octahedral. Both the molecular geometry and the electron geometry are the same. The reason why it is called octahedral is because you have 4 sides on the top and 4 sides on the bottom. As it's totally closed, it forms an octahedral. But if we remove 1, it's interesting, you get 5, but you add a lone pair. Okay, so this one is fairly interesting, and as you can see, if I turn it around, as you see, this 4 is roughly maintain the square configuration, and with 1 perpendicular to it. So in terms of the electron group geometry, this is called octahedral, but as molecular geometry, this is called square pyramid. It's a pyramid, and then you can have a square. The bond angle here slightly less than 90, but very little difference. So sometimes some textbooks kind of ignore it, as they call it a 90 degree bond angle. So how about take away another one and add another lone pair. And now if I rotate the molecule around, now you can see actually now it is the 4 surrounding atom will be situated on the square. So it's called a square planar for the molecular geometry. The electron geometry is still octahedral. How about keep on taking this one away and add another one. And now you can have a T-shaped molecule, but those are rare. The common ones will be taking away 1 and adding another one. So now we have another linear molecule. This is molecular geometry is linear, electron geometry is still octahedral, because those 4 pairs are now lone pairs. It's not shared with anybody else. So in a case, let's take a look at some real molecules. If we can have this Z on F2, because this has the AB2E3 notation, and this is a linear molecule. It's 180 degrees. So you're highly encouraged to come and play with this molecular shapes simulation. So let's switch back to the presentation. As we see this before in the simulation part, you have electron group that is let me work this one out. I have an electron group. We have 2 electron group number will be 2, and you have a linear electron group geometry. So we talk about electron group. You have a linear, and if the both of them are connected, and this is going to be molecular geometry. Let's organize it a little bit better. Let's erase this and call this one electron group geometry. And this one is called molecular . As you can tell, the bond angles will be 180. Continue the discussion, and now we have this we have 3. Now I have the electron groups is 3 trigonoplanar. Just ignore the sp2 because we were going to discuss about that later. It's called hybridization. If we have 3 of them all connected with surrounding atom, we now have this trigonoplanar molecular geometry with the bond angles at 120 degree. And the other situation would be the AB2E1. If we have a lone pair, on that, the electron group geometry is still trigonoplanar, but now this is a slightly less than 120. It's about 118 degree in bond angle. So this is actually called bent, because only those are counted as the shape of the molecule. The lone pair is part of the central atom. So continue discussion. If we have 4 electron groups, this is tetrahedral, and if we have all of those electron groups connected to the surrounding atom, now we have a tetrahedral shape, and with the bond angle is 109.5 degree. It's 109.5 degree. However, if we have you have a single lone pair on the central atom, so now the shape of the molecule is becoming trigonopyramidal. It's a trigonopyramid. It's triangle and it's a pyramid. And also because of the effect of the lone pair, and this is going to be squeezed down, so it's slightly less than 109.5. It's about 107 degree. About 107 degree. So now you see the last case for an the electron group is 4, Now I have two lone pairs, one is here and one is here, and now it's the electron group geometry still tetrahedral, but not only these two are connected with the central atom, so the shape of the molecule will be bent, and this angle is even smaller than 107, so it's roughly about 104.8 degree. 104.8 degree. And now you can start seeing the trend, and the shape is primarily determined by electron group geometry, and then you're looking at how many of those electron groups are connected with real atoms, and then you have to take into account of the effect of the lone pair. It's pushing down everybody a little further. So then when you have 5 electron groups as shown here, and if all of those electron groups are connected with atom, now form a perfect trigonal bipyramid. You see a trigonal here, it's equilateral triangle, and I got these two bonds to go directly through it. So you have two bond angles, so those are 90 degree, but between those it will be 120 degree. It's called trigonal bipyramid. But now if we have one lone pairs, if we have one pair of the unshared valence electron in the central atom, now we're going to have 4 connections, as we saw it in the simulation. It's called a seesaw, and in this case it's called a sawhorse. Okay. So because of the effect of the lone pair, it's slightly less than 90 and slightly less than 120. So we kept that going. If you have 2 lone pairs, and now you have a T-shaped molecule. If you have 3 lone pairs on the central atom, now you have a perfectly linear molecule, and with 180 degree, we call the bond angle. And in this case, we're going to be slightly less than 90. And for this one, it's going to be slightly less than 90 and 120 degrees. Okay, 120 degrees is between those two, 90 is between those. Okay, so that's about the electron group equals 5. And now take a look at the electron group equals 6. And if you have all of those electron groups connected, you will have octahedral. Then all the angles here will be 90 degree. And if you have one that is lone pair, now you have what we call a square pyramid, and this is the square, and this is the one going perpendicular to it. As we say, the lone pair effect will make it slightly less than 90, ever slightly. So now if we have two lone pairs, 2 pairs of lone electrons are shared, and not shared. So now you take out this 2, now you have a square. So it's a square planar molecular geometry. As we proceed with 3 lone pairs, now you have T-shaped, slightly less than 90 degree for those bound angles. So the last one will be the AB2E4. If you have 4 pairs of valence electrons on the central atom, you will force the other 2 go straight. So then now let's take some real examples and actually guide you through the whole process of determining whether the molecule is polar or whether the molecule is shaped like trigonoplanar, linear, tetrahedral, or the other shapes. So the process starts. Let's take a look at the real example. How about hydrogen cyanide? Let's change the color hydrogen cyanide, if you go through the whole steps, and you will arrive at the first most important step is get the Lewis structure. You will have this. That's the correct Lewis structure for hydrogen cyanide. So this one will be AB2E0. Electron group geometry will be linear. And molecular geometry, as we can see here, is connected with N, carbon is connected with N, carbon is connected with hydrogen, and then this one will also be linear. Okay, so that will be the ultimate. This is the shape of the molecule. Hydrogen cyanide is this. Hydrogen cyanide is this. It's linear. The other thing is, now let's take a look at BF3. BF3, linear, the bond angle will be 180. Okay, the bond angle is this. It will be 180. BF3, long story short, you will see the Lewis structure. 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is AB3E0, and you will have, as you can see, the electron group geometry. You will be trigonal planar. Okay, and because all those electron groups are connected with fluorine, the molecular geometry will be the same, and the bond angles should be 120 degrees. Should be 120 degrees. Okay, and take a look at the other one. Will be nitride ion, and as you can see, going through all the steps of writing proper Lewis structure, and this is what you're going to get. And it's -1 charge. It's -1 charge. In this case, it will be AB2E. The total number of electron groups is 3, so you should have some trigonal planar. So it's trigonal planar. Trigonal planar for the electron group geometry. However, they only have 2 linked, and the molecular geometry will be bent, and the bonding angles in this nitride ion will be less than 120, and it's approximately 118 degrees. And as all you saw, the CH4, and that's what will be tetrahedral all the way. Tetrahedral for electron group geometry, and this is also molecular geometry. It's also tetrahedral. And now getting a little bit interesting, and H3. This one is going to be AB3E1. Electron group is still same, tetrahedral, but the molecular shape is different. Now we have trigonal pyramid. So this one is called trigonal pyramid, classic example of water, and you will see that one will be AB2E2. And this one will be the electron group of tetrahedral, and the molecular geometry will be bent. And the trigonal, this one is tetrahedral. The bond angle is 109.5, and trigonal pyramid is slightly less, it's about 107.5. And this one is it's bent. The bond angle is even smaller, 104.5. Not degree, what I'm talking about. this. It's just degree, it's enough. Okay, so, and you can see the whole process. Let's reiterate. You take the molecule polyatomic ion, you write the proper Lewis structure, go from the proper Lewis structure to the ABXEY notation, and go from there. The electron group geometry will be determined by the strong repulsion between those electron groups. And then you're looking at how many of those electron groups have to be connected with the atom. So where you can have additional molecular geometry comes in. Molecular geometry comes in with lone pairs on a central atom. So the one, you can see PF5. This one will be AB5. This one will be trigonal bipyramid. Molecular geometry will be the same, and the bond angle will be 90 and 120. But if you have SF6, SF4, for instance, you have SF4, and you will have SF4, you will have, long story short, you have S, F, 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 you have a pair of electrons on that. So this one will be AB4E1. Still, electron group geometry determined for this is trigonal bipyramid. However, we're having a lone pair, we're missing one, and now you're going to looking at S, F, 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 F. You can call it a seesaw. Or seahorse. Okay, so then the bond angles will be slightly than 90, also slightly less than 120. Okay. Continue on that. You can have, for example, the XEF2, the Xeon difluoride, difluoride. So if you get the correct Lewis structure, will be XE, F, F, 1 pair, 2 pair, 3 pairs on the central atom. So this is AB2E3. Electron group geometry is still trigonal bipyramid. However, the molecular geometry changed, and now it is a linear. So the bond angle is 180 degree. So the 180 degree. So the list goes on, and let's take a look at it quickly for the SF6. You're going to say this is AB6, and everything will be octahedral, and molecular geometry will be octahedral, and all the bond angles will be 90 degree. But if we go into the BR F5, and you will see this one will be BR F, 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 F. Now have a pair of electrons on that. So this one will be, in terms of electron group geometry, octahedral because we still have 6. But from the molecular geometry, this is we're going to be square planar. And this is going to be slightly less than 90 degrees from the bond angle, slightly less 90 degrees from the bond angle. And you can do the other examples. So then before we wrap up this vodcast, let's recap. And the importance, the simplicity of the VSEPR theory is utilizing the strong repulsion between the electron groups. So they assumes a certain shape, and then those you can looking at those electron groups, how many of them are connected to the surrounding atoms, and that determines the overall shape of the molecules. But still remember, the underlying determining factor is the electron group, is the strong repulsion between the electron groups. And with that, I'm wrapping up for this podcast. Do not forget to complete the assigned worksheets on molecular geometry. Thank you very much for your attention.